stream me. I mean, you really want to hear this guy. Good evening, ladies and gentlemen. I'm Ben Dorman. I'm the chair of the Friends of the DAO. Thank you for coming tonight on our last night of the regular season. We are going to continue into the fall with one star party every month. The next one is going to be our annual general meeting. If you're members, I hope you show up and make sure that we vote in legal stuff. Before I go on, I should acknowledge that we are on the land of the Senchothan speaking peoples, the Sartlip, Saout, and Sekum peoples of the Wasanic First Nations. So we are lucky to have Simon here this evening. Simon is a graduate of the University of Toronto, and he's a bit of a hybrid. He's got a in two different ways. He's got a degree in astrophysics and chemistry, and from that other center of the universe back in Ontario, I forget, begins with T. And he's also working with both a scientist from the Dominion Astrophysical Observatory and also from UVic. He's going to tell us about dwarf galaxies, which he calls small towns in the cosmic countryside. Most of you know what galaxies look like. Well, these look nothing like any of those. So I'm not going to tell you any more about it because he is, but you're in for a treat. Thank you.
Yeah, thank you. All right, folks. Thanks so much for having me, and thank you, Ben. Thank you, everyone who's here in the crowd tonight, and thank you, everyone tuning in on the stream. I'm really thrilled that I'm here speaking to you this evening. So I'm going to be talking about dwarf galaxies, as Ben mentioned. And really, these galaxies, as you said, are unlike anything that we are familiar with in terms of galaxies. They're much smaller and they look much different than anything we might be seeing on some of these posters around the room even. I think the second poster out and then the last poster at the end, those are examples of big, large galaxies, some of which I'll be showing up on the screen in a moment. But before we can delve into that new type of galaxy, this dwarf galaxy that we don't know too much about, let's start somewhere a little more familiar with our own Milky Way Galaxy. We don't see the Milky Way from a distance like we often see galaxies in these beautiful images from massive telescopes, but rather from within the Milky Way. We see this beautiful swath of stars across the sky on a clear night. Now, the Milky Way is actually quite close to two other large, fairly recognizable galaxies that you may have heard of in the past. Now, before I show you those, I think it's important that we know what a galaxy is. There's many different definitions of a galaxy, and that definition is still debated in academic circles for sure. But tonight, we're going to take on this definition, that a galaxy is a collection of stars bound together by gravity. Stars that are all orbiting together with gravity, that are holding themselves together with the mass that makes up that galaxy. Now, the two nearby galaxies I mentioned before are the Andromeda Galaxy and the Triangulum Galaxy. They're two of the most brilliant objects in the sky with a modern telescope, and they've helped inform us as to what a galaxy really is, being a collection of stars. And it's likely that the Milky Way, seen from a distance, looks quite similar to the Andromeda Galaxy with this bright, bulging center and these blue kind of spirally concentric features coming out from them. But again, these galaxies, they are somewhat familiar to us, and they're in our little corner of the universe, our little local world. But it's important that we learn about where we are, not only with respect to Andromeda and with Triangulum, because it's within this region, within this neighborhood of the universe, that we're going to be learning about dwarf galaxies tonight. First, to get ourselves situated, we're going to do just a fun little example of how we can situate ourselves in the universe, as if somebody were to send you a letter this evening at this very hill. They need to write down your address, the address that we are used to writing on letters, licking a stamp and putting it on. Here at the hill, we've got an address of the center of the universe, 5071 West Saanich Road, Victoria, British Columbia, Canada. And I've added an extra line that you probably wouldn't have to put if you were sending a letter to your friend. But we are in North America, and we are on planet Earth. Now, if we wanted to send a letter, or if somebody wanted to send a letter to us from across the galaxy, there's a bunch of other qualifiers that we can put in there to help localize ourselves within the universe. We are the third planet from the sun in the solar system, this local home where all the planets that we know well are orbiting the sun. And we are in what's referred to as the Orion Spur of the Milky Way Galaxy. Now, this image was not taken by a telescope. It's been constructed from what we see looking out from planet Earth. But we think that the sun is about 2/3 of the way, about halfway out from the central region of the Milky Way. And it's near to this structure within the spiral arms of the Milky Way called the Orion Spur. But taking one further step back, if somebody was sending us a letter across the cosmos, we would have to keep adding more and more and more lines to this address. But I think for the purposes of tonight, we need to add just one more. And it's a line and a region and a corner of the universe that we're going to get to know pretty well this evening. And that's called the local group. The local group is where our galaxy is, it's where Andromeda is, and it's where Triangulum is. But it's also home to tens and tens and tens of dwarf galaxies. This is just a gorgeous figure that I really wanted to show you all, that was super instructive to me even. I learned about new galaxies in our local group. And we're going to zoom right in on the Milky Way here and see everything else that's in there. The Milky Way being this, kind of a cartoony icon of this central spiral, but there are tens of galaxies surrounding it. These are the dwarf galaxies that I'm going to be talking about tonight. All of them, every single name you see here, Reticulum 2, Sculptor, Gru, all of these are tiny worlds, tiny collections of stars bound together by gravity. Galaxies in their own right that are orbiting the Milky Way in much the same way that planets orbit the Earth. These galaxies are orbiting the Milky Way. In addition to that, there is a whole swath of galaxies also orbiting Andromeda. This M31 here, that's the kind of astronomer's name for Andromeda. M33 is the astronomer's name for Triangulum. And as you can see, there's plenty of dwarf galaxies orbiting that area as well, with much less creative names, A28, A11, I don't know. However, these galaxies are the galaxies we'll be focusing in on this evening. If you had a keen eye, you can see there's a bunch of other things kind of in this corner, down near the bottom. I'm not going to be focusing on dwarf galaxies that are a long way from the Milky Way. If you'd like to know, the name for those is isolated dwarf galaxies. But tonight, we're just going to be focusing in on the galaxies that orbit the Milky Way and the galaxies that orbit Andromeda. Now, for a sense of scale, the Milky Way is a pretty big galaxy, all things considered. If we look out into the cosmos and compare to all sorts of galaxies across the universe, the Milky Way holds its own. There's certainly some that are bigger, there's certainly some that are smaller, but it has about 100 billion stars that make up this body that is bound together by gravity and orbiting. In these dwarf galaxies, in particular in the smallest dwarf galaxies we know of, we believe they have something closer to 100,000 stars, maybe even less. So some of these galaxies are 1 million times smaller than our own Milky Way. I'm not going to show you any pictures quite yet. Well, we're going to go through, as you see, but what I'm going to go through next in the real kind of meat and potatoes of this talk is going to be the history of how we've been able to detect such small, faint collections of stars kind of just outside in our backyard in the local group. This history comes along with incredible advances in technology, advances in the understanding of stars and their behavior, and advances in the understanding of galaxies. These dwarf galaxies are the weirdest galaxies that we know of. They're the smallest collections of stars that are somehow held together by their own gravity. And tonight, we're going to get to meet, in some sense, just about all of them that are orbiting the Milky Way and Andromeda. Now, the first two galaxies that we're going to talk about are surely the most famous, as they've been known about, as we expect, for as long as human history. These two clouds, these two murky bluish purple clouds over here, are full galaxies in their own right, and they're just outside the confines of the Milky Way. They're known as the large and the small Magellanic clouds. They're actually pretty big. All things considered, I think the large is something on the order of 10% the size of the Milky Way, and the small 3 or 4% of the size of the Milky Way. But they're so bright, you can see them in the night sky. That image that I showed first, it's a long exposure, maybe a couple minutes. But if you were in the southern hemisphere, you could absolutely see those alongside the Milky Way on a clear night. For that reason, we believe they were known to all pre-modern peoples indigenous to the southern hemisphere of the world. But they weren't written about in science, in astronomy, until 964, a millennium ago, when a Persian astronomer by the name of Al-Sufi first wrote about them, noting that he could only see them when he traveled in the south part of his country or into kind of the northern, southern part of Africa. Knowledge of these galaxies didn't come to the Western world. The world from which our modern science has mostly grown didn't come to the European world until the early 1500s, as you can't see these galaxies in the northern hemisphere. None of us could go outside tonight and see them with a telescope. They're hidden behind the horizon, south of the equator. The first European we believe to have seen these galaxies was the Italian explorer, a contemporary of Columbus, Amerigo Vespucci, who wrote about them on his travels across the ocean. And it is not a coincidence that Amerigo sounds like America. That is where the name America was derived from, a little factoid. But again, a little naming factoid is that the explorer who really brought them into European main knowledge was Fernando de Magellan, of whom they have been named after, the large Magellanic cloud and the small Magellanic cloud. It was his writings on his voyages that brought them into mainstream European science in the mid to early 1500s. Now, these are big, unbelievable galaxies. You can see similarly, in some sense to the Milky Way, these pink and blue features that you might see in bigger galaxies out in the cosmos. But the next set of galaxies we're going to look at are truly the first dwarf galaxies that act like the dwarf galaxies I'm going to be talking about for the rest of the evening. The next technology that we needed to be able to see such faint systems was photographic plates. They work on very much the same principle as a film camera. You've got a surface on which there are chemicals. As light strikes those chemicals, it interacts with the chemicals and produces dark patches on your photographic plates. They then have to be developed, again, in a similar way to film camera. But what we see instead is stars show up as dark patches where these chemical reactions have occurred, and the white patches are the blank sky of the cosmos. Now, using photographic plates, the first dwarf galaxy, other than the large and the small Magellanic clouds, was the galaxy Sculptor that was discovered in 1938. And over the course of about 6 decades, 9 more of these dwarf galaxies were discovered. Now, this is the Karina dwarf galaxy. Looking at this image, I would understand if you don't quite believe me when I tell you there's a galaxy here. It's just a whole splotches of light, or in this case, darkness. But what I hope to convince you of on the next slide is that this kind of central region here is in its own right an entire galaxy. Hundreds of thousands of stars, probably millions of stars in Sculptor this is Karina, sorry, held together by its own gravity in its own right. This image is not a photographic plate, but this was the first galaxy discovered, Sculptor, in 1938. And what the authors did is they took their photographic plate and they went through by hand and they marked down the precise positions of all the stars on that photographic plate and transferred it, in this case, to a piece of paper. And now we can start to see what they mean by there being some kind of structure there, right? In the middle, clearly, there is this clumping, this density of stars, unlike anything we're seeing along the edges along anything we're seeing along the bottom, there's a lot more stars in the middle of this image than there are on the outskirts. These were the first galaxies, these first dwarf galaxies that we saw in modern astronomy. To compare this to a contemporary image from the European South Observatory, we can start to see what modern dwarf galaxies really look like. They're more so characterized, not like the Milky Way with those bright spiral arms, but by a clustering of faint stars all together in the middle of your image, where there's a soft, faint glow of often yellow or reddish light. They're typically a spherical shape or an oval-like shape. But there's none of these bright spiral features, none of this bright gas or dust or new fresh stars. All the stars in these galaxies are old, likely older than 10 billion years old. Galaxies from the very beginnings of the universe that have been dormant, that haven't been forming stars all throughout cosmic time. Now, following the photographic plates and the limitations presented to us by trying to detect light with chemistry, in the early 80s into the 90s, we started to develop the technology of digital cameras. And digital cameras, in some of their first editions, were designed to be put on large telescopes. Now, these digital cameras saved us a lot of grief. We no longer have to go and develop the film to be able to see the stars. You can save the data immediately, but they don't solve one of the great questions in trying to find dwarf galaxies, and that is, where do we look to find them? All those 9 dwarf galaxies I talked about before were found through a combination of incredibly detailed inspection of astronomy results, through ingenious insights as to how stars behave and why they should cluster like that, and pure luck. That is absolutely not to belittle the accomplishments of those previous astronomers, but actually to lift them up, in that looking over the entire sky, they managed to take these images and recognize amongst those smatterings of stars that they were seeing entire galaxies out beyond the edge of the Milky Way. So these digital cameras have afforded us now the ability to look more into the sky with more rapid data storage, but they don't solve the problem of where to look. Well, they actually do. The answer to where do we look is everywhere. The Sloan Digital Sky Survey, this absolutely epic telescope over here, is a telescope, it's built on a mountain in New Mexico. And it was one of the first electronic telescopes developed to do what we would call today survey science, as the name of the survey suggests. The survey science being that this telescope could now take pictures of huge expanses of the sky, not looking for specific objects, but just kind of checking out the whole sky over the course of years and years and seeing what we found at a later date. The electronics are much more rapid than the chemicals that we would have used to develop those photographic plates. Large amounts of data coming off the telescope can easily be stored quickly and efficiently for use at a later time. And lots of the sky can be seen over the course of a long period of time. Well, really a short period of time. And the key theme that you may have noticed throughout this is speed. Digital telescopes sped up astronomy by orders of magnitude due to the lack of kind of manual extra steps we had to add in there. SDSS, which I'm going to call the Sloan Digital Sky Survey, SDSS covered about 11,000 square degrees of the sky, which is 27% of the entire sky all around the Earth. One way to think of the sky is that we are inside of a sphere and we're looking out onto the inner walls of the sphere. In order to try and visualize that in a 2D sense, you can kind of plaster it onto this oval, and everything within this oval is the entire sky that we see. 27%, that might sound like a lot to you, that might sound like a little. I think there's a very interesting comparison that may help you understand what this meant for astronomy. All of the dry land on the surface of the Earth covers about 30% of the surface of the Earth. The imagery taken by SDSS was equivalent to taking the best high definition, high resolution imagery possible in the early 2000s of every square meter of the surface of the Earth, and just looking through it, digging through it, seeing what new astronomy we could find. This survey was actually initially designed to look for galaxies out in the universe well beyond the confines of the Milky Way and map the cosmos that we see. But it accidentally was really, really good for dwarf galaxy discovery because it mapped the positions of every star in the sky down to a certain sensitivity. The first dwarf galaxy was found in the SDSS data in 2005. And throughout the next half decade, 14 new dwarf galaxies were discovered, more than doubling our current known total, all because of this initial digital camera that was pointed up and let to scan the sky for about 10 years. Now, this work has been continued by plenty of other telescopes. The SDSS is still in use today, though it doesn't do this big sky scanning anymore. But other telescopes kind of took up the charge in many different capacities, telescopes that take incredibly deep imagery. The three that I'm going to mention tonight are programs occurring at these telescopes. So the Dark Energy Survey is occurring at the Victor Blanco telescope in Chile in the Andes. The Pan-STARRS telescope and the Canada-France-Hawaii telescope are both initiatives taking place on mountaintops in Hawaii. I would like to talk about the Canada-France-Hawaii telescope for a couple minutes on its own, as tonight, we're not only here at the center of the universe, but we are also on the same grounds as the Dominion Astrophysical Observatory and the National Research Council Astronomical Institute here in Victoria, one of the federally funded institutes across Canada, and the place where I think it's fair to say the most astronomy goes on in the entire country. There's tens of astronomers working down at NRC, maybe even 100 astronomers or more, all working towards producing astronomical innovations for anybody to use. Now, NRC members, so NRC is how I'm going to refer to it. NRC members have always been incredibly vital to the runnings of the Canada-France-Hawaii telescope, which is, I believe, 1/3 run by Canadian astronomers. In particular, I can give a couple examples. Sidney Vanderberg was one of the former directors of the NRC in the late 70s. And he went on to serve as the president of the CFHT board, this telescope. And plenty of NRC staff today do incredible data storage and data processing at CFHT. And in a couple slides, I hope I can at least impress upon you the amount of data that comes out of these telescopes. It's absolutely mind-boggling as to what has to be done to the information coming out of those telescopes to make it usable and interesting. In addition to this telescope being a Canadian venture, the Pan-Andromeda Archaeological Survey, which I think has a great acronym in PANDAS, was an international team, but led by astronomers here at the NRC, as well as having several astronomers from the University of Victoria along with the crew. It ran for 4 years, from 2008 to 2012. And it was focused in on the region around the Andromeda Galaxy. There had been a couple bright dwarf galaxies identified in that region of the sky orbiting Andromeda before this, but this venture found 15 or more new dwarf galaxies in that area. Once again, continuing to exponentiate the total amount of galaxies known. Now, bringing us back to this image of Andromeda that I think I included earlier on in the show, we can actually see two dwarf galaxies right here on this image. These two bright patches of light are dwarf galaxies in their own right, galaxies that were discovered, I believe, long before PANDAS was completed. But these are galaxies, and for anyone curious, these bright patches up here are likely stars that are within the Milky Way. Because when we look out and we try and take astronomical observations, we can't just move the stars in the Milky Way to get out of our way. There's lots of bright stars in any path of light that you take. Now, due to SDSS, the Dark Energy Survey, Pan-STARRS, CFHT, and several other ventures, we have identified more than 30 dwarf galaxies orbiting the Milky Way. and nearly 70 dwarf galaxies in orbit. Sorry, yeah, 30 around Andromeda, nearly 70 in orbit around the Milky Way. Many of these coming in the last 20 years since the advent of digital cameras. The next slide, I do just kind of want to leave up for a moment or two. Here are several dwarf galaxies that have been found over the past 20 years. And finally, some images that you guys can really sink your teeth into. Some of them are much more obvious than others, for sure. Like Bootes 1, found in SDSS, a clear, bright collection of stars. Eridanus 2, these blue highlighted stars make up the main body of the galaxy. But even still, it's kind of hard to tell there's a structure there. But we know, based on other properties of these stars, other observations, that these are all gravitationally bound together. Some of them are absolutely nuts. Like Leo 4, I've looked at this thing for hours. I have no idea where the galaxy is. I know that the Hubble Space Telescope took this image and was pointed at this area of the sky. And based on other properties of the stars, they're there, they're connected together, they're orbiting each other. But man, some of these things are just so faint. Even Levin's 1 kind of looks like a really faint version of Sculptor, maybe. The last one I included is here from the Pandas survey, this Andromeda 21. Couldn't find any good images of it, but it demonstrates a little bit of how we detect these things, similar to how the very first dwarf galaxy was detected. Taking all the stars and plotting them on a sheet and looking for places where more stars are grouped together. Now, this is a bit of a funny one because there's also this kind of missing chunk of data right between. But even still, it's quite clear that there's a lot more stars in the middle of this image than anywhere else. Sorry. For the last few minutes of this talk, I'm really excited to share this with you folks. This is the field that I work in. I've been doing this for the last year as a part of my master's research. And I'm going to show you guys some real data that's come off of these real telescopes and how people, astronomers, researchers find dwarf galaxies today. So as a quick background, the work that SDSS started, doing these surveys of the entire sky or big chunks of the sky, is really the way to find dwarf galaxies. The data that I work with is called the Ultraviolet Near-Infrared Optical Northern Survey. And it's a group of several telescopes on the islands of Hawaii that have combined their resources to make incredibly sensitive images of big patches of the sky. In particular, my work has been with this, the Pan-STARRS telescope that I mentioned previously, and the Canada-France-Hawaii telescope. So much of this work is about data. Is it about handling data, storing data, somehow sifting through data? I had to work with some of this kind of at the start of my project to make it ready for use. And I basically essentially had 2 Excel spreadsheets, each of which were like 500 gigabytes, like hundreds of millions of rows, like 70 or 80 columns across, just gargantuan files. It was crazy. Couldn't even store them on my computer. I had to store them on like some supercomputer somewhere. But I want to show you some of this data because I think it's really amazing to look at it and understand, especially what the early astronomers in the early parts of the 2000s were doing when they first got their hands on electronic data. This is a patch of the sky. It's about a third, I think about a third of what I've been working with. And the white that you see is the individual sky positions of every star observed by this survey. That's the reason we're seeing kind of cloudy bits in these holes. That's because there's a lack of stars there. Everything else is made up of tiny, tiny, tiny dots, each of which are individual stars in the sky. These weird kind of like tracing patterns as these big missing things are things that the telescope just didn't observe. But this is a huge chunk of data, more than 15 million stars, all spread out across the northern sky. I'm going to zoom in on a couple regions to illustrate a little better what I'm showing you here. This region in the upper right, this region down in the lower left. The first I'd like to show you is this galaxy. This little patch in the middle of stars. This is DDO 99. It's actually one of those isolated galaxies I briefly mentioned at the start. This one is not orbiting the Milky Way, but it is a galaxy in its own right, actually a pretty huge galaxy. And zooming in on it, these are the stars that the telescopes have detected, and these are the stars that make up its body. And even looking at it, that you could have seen on this big patch of sky, it was obvious that there was a big clump of stars right in the middle of the screen. If you're curious, this weird little patch in the middle that's missing is because this galaxy is actually really bright and overloaded the really sensitive photoreceiver on the telescope. So that's why there's a little hole. But everything else you see, all these other stars are very likely to be stars that are part of the Milky Way. Stars that we have to look past, that we have to look through to be able to see these other objects way, 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 way deeper in space. The next one I'd like to show you is this Willman 1. And this is using the data that I'm working with. Willman 1 was that first galaxy discovered in SDSS in 2005 by a researcher, Beth Willman, whose research group went on to discover 5 or 10 of these things. It was an incredible piece of work that they did. But this is Willman 1 in the Unions data set. And then I kind of messed with it a bit to see what it would have looked like when they were looking with SDSS with much less sensitivity. And it would have looked like this. These are all still stars. It just looks way less bright because there's probably only about 5% of the stars that I showed you initially. You can still see this bright patch in the middle, but it's pretty amazing that they were able to look at this for the first time with digital information and know that that was a dwarf galaxy, a galaxy held together by its own self-gravity beyond the edge of the Milky Way. There's one more that I want to show you. I'm really honored and I'm really humbled to get to share this with you guys. On this image, there is a galaxy. Some of you may have spotted it already. I'll zoom in a moment, but I'll let you take a look at this. All these patches of stars for a moment. The galaxy is here. This patch of maybe 30 stars, 10, 20 stars, bright stars. I'm really excited to tell you guys that this was a galaxy that I found at the start of the summer as part of my master's research. Oh, thanks. It was really, really exciting to see this. And I'll show you one other slide from my paper. I'd like to highlight as well, amazingly, I found this galaxy at the start of the summer. Another researcher, another student by the name of William Cerny, working in Chicago using a different set of data, also found this galaxy. We found it within like 2 weeks of each other, which was amazing. And we got to collaborate. We didn't write the paper together. We wrote 2 separate papers, and we've both been working on those over the last few months. But it was really special to get to share this and to collaborate with this other young scientist. But this galaxy, which I've now kind of really zoomed in on, is this central patch of stars here. And this image is from the telescope, from the Canada-France-Hawaii telescope, just in black and white of, oh, there we go. Just this central part here. These bright, bright stars are definitely part of the Milky Way. These are all Milky Way stars. And then this like just barely visible central patch of light is again, an entire galaxy of stars held together by its own gravity. It was found in the constellation of Bootes, and it was the 5th one there. So it's Bootes 5. And thanks for letting me share this with you. To finish us off tonight, I just want to bring it back to this image. And I hope in getting to learn about dwarf galaxies tonight, you've also come to think of this, the local group, as our home. And it is. We think of the Earth as our home. And in a bit of a more astronomy sense, we think of the solar system as our home and the sun as our own, for sure. But in galactic terms, this is our neighborhood. This is where we live. We are, living in the big city of the Milky Way with the other big cities, Triangulum and Andromeda nearby, and all these other small patches of light, all these other tiny towns, these faint collections of stars all around us are all part of our home as well. So thanks for coming. Thanks for learning. Thanks for listening. Thanks for being here. All right. I actually think our host, Ben, has left. Does anybody have any questions? I think we have like 5 or 10. Yes.
Thank you very much. Yourself.
Thanks.
I'm curious about the other qualities that you identify more galaxies that it's explicit. And basically, you said if you're bunched together, that's a likely characteristic, but there are other features.
Absolutely.
So, say something about features.
Totally. And by the way, should I re-answer that for the stream?
Sure, yeah.
Yeah. So I was asked about what other features of the stars, what are the features of the groups of stars make us believe or make us inclined to think that this clump of stars might be a galaxy, which is a great question. And that is a lot more of the nuance of finding these galaxies. There's a couple different features that go into it. One of which comes from a telescope that's out there in the cosmos doing its thing right now. That's called Gaia. And what the Gaia telescope does is it is constantly scanning the sky for all the stars that it can see and measuring how they're moving on the sky. These teeny tiny, very precise movements on the sky are being measured by Gaia. And in doing so, some things that we've discovered are different structures about the Milky Way, different things about galaxies near to the sun. But what we can also see is when we identify a bunch of stars in our survey, in the Union survey or SDSS, we can go and check Gaia. And if all or most of those stars are moving in the same direction at the same speed, that's a good hint that they are gravitationally bound and all moving together through the cosmos. Whereas all the other stuff in front of it will be moving this way or that way all over. It is, which is unbelievable. I do believe that Gaia picks up some of the stars in Andromeda. It's not as precise at those distances, and it doesn't really pick up stars in other galaxies past that. But amazingly, it is picking up stars in galaxies just outside the Milky Way. Yeah, great question. Anybody else? Yeah.
Yeah, this is a question from the audience.
Great.
Since you discovered the galaxy, do you get to name it?
That is an awesome question, and I wish I did. I'm going to go back a couple slides here. So Beth Willman, who discovered this galaxy in SDSS, definitely pulled the pro move and named it after herself. Well done. Typically, if you're up to date on your astrology, you may have noticed that a lot of these names, got to go through my transitions. A lot of these names, like Sculptor or Gru or Horologorium, all of these are actually names of constellations. And the way that these galaxies are typically named is what constellation in the sky they are closest to, plus a Roman numeral saying how many other galaxies. Bootes 5, this galaxy is the 5th one found near to the Bootes constellation. So that's how it's named. Yeah, unfortunately, not Smith 1, but that's a pretty boring name. So I'm okay with that. Yeah. Yeah. Oh, that is a great question. That is a great question of active research. I think the best answer I can give right now is to say that all galaxies, for the most part, formed initially out of a big cloud of gas that collapsed in on itself due to gravity and then started forming stars. And those stars then started living their lives as stars do, like our sun does, for instance. So the Milky Way was once a huge cloud of gas that collapsed in on itself, formed billions of stars, started rotating around itself. These small galaxies would have formed, we believe, from small clouds of gas that condensed down and formed maybe 100,000 stars, 1 million stars. But the key difference is that because these galaxies are so small, they have a much harder time holding on to any gas that remained after those first stars formed. So in the Milky Way, all the gas is still able to form stars. We're able to pull in new gas because of our gravity and form new stars. These little galaxies couldn't pull in new gas. Even the gas that was in there might have been blown away by winds between stars. And so what we observe and what we're basing our theories on is that nearly all of these galaxies haven't formed stars in the last billion years. And so they couldn't hold on to that gas. Yeah, that's a great question. Anybody else? Yeah, right on.
I still have a couple of questions. One is, you mentioned Andes and the archaeological.
Yeah.
And the other, one other question is concerning a dwarf galaxy that you named Ursa Minor. That's a constellation out there. So the constellation really is dwarf galaxy.
Sorry, no. So the constellations, my apologies. I think I explained that poorly before. Constellations on the sky are, made up of bright stars that we can see, that astronomers have just gone through and said, this region of the sky belongs to the name Ursa Minor. So that galaxy would have been found somewhere in that box on the sky nearby to it. It's very unlikely that you could see any of the stars in these galaxies. They are extremely faint because they're so far away. Yeah. Yeah, that's another really good one. We believe that the Milky Way itself was not a single cloud of gas that collapsed, but rather several large clouds of gas that collapsed and then at some point in the past merged together to create one new, bigger, stronger galaxy. The archaeological in that name comes from the fact that being able to observe these stars and lots of other properties of these stars is potentially allowing us to piece together the history of already formed galaxies. The Milky Way has been seen to likely contain 3 or 4 or more major galaxies that all collided at some point. And we can see signatures of that in the way the stars move and what the stars are made of. And so the archaeological bit comes from trying to look into the past and understand how these galaxies were built. Yeah. Yeah. Okay. I think we might have time for one more if we want. Otherwise, all right, great. Thank you so much for coming, everyone.
Okay, hi everybody. That was a great talk. We're going to talk about what's up in the sky. I'll just give a bit of a highlight of what we're going to talk about and then a couple of words from Amy before we actually get into the details of it. We're going to talk about the usual sunset, sunrise times and so on, when the planets come up and where they are. And we're also going to show you how to find the Andromeda Galaxy, which is kind of cool because this is actually the greatest time of the year to be looking for it because it's pretty much right overhead and it's quite easy to find. I'll be talking a little bit about equinox versus equilux, which is something we've talked about before, but it bears repeating. And a bit about the light pollution survey that's going on with the Royal Astronomical Society of Canada. And also it's connected to that, actually, in a way, is an opportunity to see something called the Zodiacal Light. And so it's something that's really you can only see well at a couple of times a year, and I'll explain why that is. And that's coming up in October, but you need to have skies that don't have a lot of light pollution in order to see it, and you'll see why. So anyways, Amy, I'd just like to ask you, before we get into all that, I mean, everybody's dying to know what's the product of the week this week in the gift shop. This is the important stuff.
I picked 2 things for this week. I have a new product and a product of the week. So very popular is, oh no, I've got that filter on. Oh, so no. We have these mugs that say warning, may start talking about astronomy. And they're pretty cute and they've been quite popular. So that's definitely to get. And
I might need one of those.
Yeah, exactly. And if they're being mailed, we do have boxes for mailing them. So if anyone's interested, those are there. And we have a new product, which is a memory game. And it is, well, what it says is that it's a matching game for future astronauts, terraformers, and near space tourists.
Wow.
But it has, it's a 50-piece matching game, and it comes with a little guidebook as well for the moons and the planets. So those are some of the things you can find in the gift shop this week.
That's great. Okay, well, thanks so much for that. And I think I'm going to share, I'll just talk a little bit about sunset, sunrise, and twilight and so on, just to give everybody the basics for how things are changing these days. So sunset was at 7:06 p.m. tonight, and civil twilight ended at 7:37, and that's kind of where end of civil twilight is, when you can't really walk around like you would in the daytime without maybe tripping on stuff. And nautical twilight ended at 8:14, and so that's the time when you should be off the water for sure, because you can't really see the horizon or what's in the water very well. And it's also the time when the brightest stars start to come out in the sky. And astronomical twilight ends at 8:52, which is coming up in just a few minutes. And so that's when, in the absence of the moon in the sky and so on, things are kind of at their darkest. And so, so let me just share my screen here, and I'm going to talk a little bit more about what's up in the sky. I should mention that the moon phase is basically, it's at 2% right now, so it's a waning crescent. So it's actually going to be a new moon as of tomorrow, and so in the afternoon, and so so we'll be in a moonless part of the sky, and that's actually going to be relevant to the light pollution survey we're talking about in a few minutes here. So let's talk a little bit about what's up in the sky in terms of planets, and I'm going to share my screen and hopefully share Stellarium. Let me know if everybody can see it here. And this should be, I'm just going to double check here, this should be the current time. Okay. And so this is the south, as you can see over here. And so let's just start actually with Saturn. So Saturn rose at 5:39 p.m. and it's in the south, sort of south-southeast part of the sky, as you can see right now. And Jupiter rose at 7:11 p.m. and is also sort of in the east-southeast part of the sky. And Monday is when it's going to actually be at opposition. And it's not mad at us or anything. It just means that it's opposite the sun in the sky. And you're going to hear stuff in the media and online about this on Monday, probably, because they're going to be saying, well, Jupiter is the brightest it's been in X number of years and so on. And actually, it's true. It's going to be quite bright for a couple of reasons. One of the reasons is because it's not as low in the sky at opposition as it was in the last couple of years, when it was more down in the summer constellations and starting to get up into the constellations that are higher up in the sky. But it's also near perihelion, which means that it's actually going to be at its near its closest point to the sun in January. So, and Jupiter does have a slightly centric orbit, meaning that it's not shaped precisely like a circle. And when it's closer to the sun, it reflects more light because the sun is brighter there when it's closer. So just like getting closer to a light bulb or street light, it's going to look brighter. So there's more light to reflect off its surface. So it is going to be brighter. I think it's going to get actually brighter over subsequent years as it gets up more into the winter sky, and that'll be quite exciting to see it in its glory. And hopefully we'll see it near perihelion then as well. So this is kind of a combination where it's near perihelion and also climbing up higher in the sky. So Mars actually, as you can see, is not up in the sky at this point. And in order to see that, what we have to do is advance the time a little bit. And there you can see Mars coming up. And so Mars rises at 10:12 p.m., sort of north of east, so sort of northeast, I guess you would call that. And if you look up here, you can see a little constellation, which is known as the Seven Sisters, the Pleiades, or in Japan, they call it Subaru. And so that's, in fact, why you have that logo on the car. So it's kind of shaped like the constellation there. And so in the morning sky, Venus rises at 6:23 a.m. and is lost in the twilight. So one thing that is coming up that's kind of cool is we're going to be able to see, let me see if I can get to the date quickly here. Oh. I always mess something up. I have to make one mistake here, right? So let's try this again. I might do it the hard way here. Let's bring it back down to early part of October, and we're going to change the time. We're going to change the time to the morning. And what you should see in the morning, and it's probably going to be hard to see a little bit in the twilight, is, oops, I think we're in the summertime here. Let's do that. You should be able to see Mercury coming up, and there it is. And it's super hard to see. It's almost always, it is actually always in the twilight, because it never really gets more than about 18 degrees from the sun, and the sun needs to be 18 degrees. Okay, hopefully everybody can still hear me here. Okay, and all right. So in any case, Mercury is visible only in the twilight, because the sun never really gets 18 degrees below the horizon when it's at its maximum distance. Okay, so I said I was going to talk a little bit about the Andromeda Galaxy, and hopefully we can just move back to the nighttime here, current time, and we're going to put some constellations back up. And so what we're going to see here is the constellation Pegasus, which looks like a big box of stars up in the nighttime sky. And if you look over towards Cassiopeia, which is a W-shaped collection of stars, then you'll notice that sort of halfway between the two, there's a faint fuzzy patch, and that actually is the Andromeda Galaxy. And so the way I always find it is I start by finding this big box of stars, Pegasus, and then I count 1, 2 stars out, then 1, 2 stars up, and then kind of look out of the corner of my eye. And if it's a nice dark night when there's no moon up or something like that, I'm away from city lights, I can often see this little patch, and that is the Andromeda Galaxy. And so if you hoist a pair of binoculars to your eyes, you'll actually be able to see that quite well. One other thing, I just want to talk a little bit about equinox versus equilux, and I'm just going to minimize my screen here a little bit. We had the equinox on Thursday, the 22nd, and that's the point where the sun appeared to cross the celestial equator on its way down south. And as the name suggests, that's the point at which we should have equal day and equal night. And if the Earth had no atmosphere, that's actually what we'd be seeing. But because the Earth has an atmosphere, the sun actually is always a little bit higher above the horizon than you would expect, because the atmosphere acts like a lens, and we can kind of see over the horizon a little bit. So on the 22nd, we actually had about 10 minutes more daylight than you would have actually expected. So we don't actually reach the point, which is equilux, equal night and equal day, until tomorrow. So a few days after the equinox. And so it's on the 25th. So there's a couple more reasons why that's the case, but I won't go into all of them right now. So I'm just going to stop my share here, and hopefully you can all hear me. And I'm going to maybe share another screen here. And what I want to do is talk to you a little bit about something called the Resc Light Pollution Survey. And this was, I'm just going to enter the URL here, and then we'll get it up on the screen and show you some examples. And so this was conducted about 11 or 12 years ago for the first time. And what they're trying to do is trying to map the brightness of the nighttime sky at different points in Victoria. And there's a bunch of reasons why we want to do this. Among the reasons is that that light can affect plants and animals, and it can also affect humans and our sleep and so on. So what we want to do is to be able to see if it's gotten any worse in the last decade. And so this started on Wednesday night. It was my first time doing it, but there were much more experienced people out doing it on that night, including Laurie Roach, who did many more sites. I think I did 6 observations in 2 hours, and I think she probably did about double that. But nevertheless, we started to actually get some data points about what's going on in the sky. I live near Hillside Shopping Center, and so far it seems that it's not really any worse, at least in my neighborhood. And so I'm just going to scroll down here and just pull up one of the maps from that was done back then. And so you can see that we have a bunch of dots here. The white dots means that the Milky Way is essentially invisible, and the black dots would be a perfect sky when there's no light pollution, and green dots are when it's near perfect, and so on. And if you notice, if you look around the coast here, you can see that there's a lot of orange dots, and so it's definitely better if you go down next to the water, like down near Willows Beach or Dallas Road or someplace like that, if you want to look at the nighttime sky. So Cattle Point I measured was actually about a little over half a magnitude fainter than just a spot just a little ways away. So just closer to Mount Ptolemy, for example. So this is an ongoing survey. We're doing it around the new moon because if the moon is up in the sky, it's going to add a glow. And so we can't use those observations. So we're going to try to pick some clear nights on either side of the new moon and hopefully get most of the map done. This is actually quite ambitious, and if I just use this wider map, you can see that in fact it's being done down in Souk and Machosen and all over the place. And I understand that Laurie and her group actually did most of the peninsula while I did my measly 6 little points here. So they really have it down to a science, as they say. So I'm just going to stop sharing that and actually go back to Stellarium and see if I can shift back to that. So bear with me. And so in let me just make sure I have things set up here correctly. I want to show a couple of different things to you. And I want to show something called the ecliptic, which is the path of the sun through the sky. And the planets orbit pretty close to that as well. So all our orbits are pretty much in the same alignment. And so you'll see that, for example, Jupiter is actually pretty much on that line, and so is Uranus down there. And so if we actually skip ahead to the end of October and go to the morning hours, I'll see if I can do this quickly. And you'll notice that the ecliptic is actually quite steep to the horizon there. And coming up from the horizon is some sort of glow. And that's not, this I've exaggerated it here just so you can see it, but this is actually not the Milky Way. This is actually light reflecting off of dust in the atmosphere. And so, pardon me, dust in the solar system, in the plane of the Earth's orbit. And so let me actually just change this back so it's a little bit more realistic. And I'm going to bring the brightness of the zodiacal light down. And it's called zodiacal light, by the way, not because it has anything to do with astrology, but because the constellations of the zodiac also happen to fall along that line as well. So on a very good night, this is what you might see, for example, over in the eastern part of the sky. Now, one of the problems with this is that we're also contending with light pollution. And the way I've got these settings set right now, it's as if there's no light pollution. So we're in a perfect spot on the Earth, and you look around and you go, wow, there's the Milky Way over there. And coming up from the point that the sun is going to come up, we see this glow coming up. And you'll notice, but this is actually a lot harder to see because of the light pollution. So if I just dial this up on this scale, it goes from 1 to 9. Here it is about 5, which is about like we see at my place. And you can see that you really can't see the Milky Way and you can't see the zodiacal light. So there's for example, some of the constellations of the zodiac. I prefer that we call it the ecliptic light, but I don't think I'm going to change it at this point. But it's basically because we're looking along the ecliptic into the interplanetary dust. And so let's just see what the effect would be if we were to go out a little ways away from the city and say where the light pollution isn't quite as bad, say out on the peninsula there. Well, if you kind of look out of the corner of your eye, you might see kind of a wedge shape sticking up from the horizon. And you can differentiate it from the Milky Way because the Milky Way will always show more structure. And you can also differentiate it from the sunrise glow because that will have some color, whereas this light is actually bouncing off of dust that's way off in space. And so it has nothing to do with the sunrise and sunset colors. So it will be a pale, unstructured color in the sky. So that's a challenge for everybody. I hope you can see it. I've seen it a few times, and it is very difficult to see, but it does bring to the forefront how important it is to have a view of the sky that's not affected by streetlights in order to see some of these astronomical phenomena. And one last thing, one little bit of trivia is that there's a well-known musician who did his PhD thesis on this, and I wonder how many of you actually know who that is. It turns out it's Brian May of Queen. And so back in the 1970s, before Queen got big, he started his PhD thesis about the origins of the Zodiacal Light. And then the band got really popular and he put his PhD aside and he finally went back and finished off the PhD, I think sometime in the last decade. So that's what he's famous for scientifically. So I think I'm going to end it there, and hopefully everybody heard that because my microphone, my headset died partway through that. One of my infamous technical problems. But I hope that was interesting. And if you have any questions, please put them in the chat, or open up your microphone if you're online with us on Zoom here. Are there any questions? Oh, okay. You actually heard that. That's reassuring. Thanks, Anne. Okay. Okay, are there any other questions? Anything about seeing things in the nighttime sky? Okay, thanks for sticking around tonight, Jim. And I guess we'll end it there. So thanks very much and keep looking up in these difficult times. See you next time.